Welcome to Math for Sleep. It's lovely to have you here tonight. Before we begin this gentle journey through the corridors of mathematical mystery, I'd love to know where in the world you're settling in from. Maybe you're nestled in a quiet bedroom with the curtains drawn, or perhaps you're stretched out on a comfortable couch with a soft blanket pulled up to your chin. Wherever you are, I hope you're comfortable, safe, and ready to drift through one of the most captivating stories mathematics has to offer. If you enjoy these relaxing explorations into the world of numbers and would like to hear more, a like and subscribe really helps this sleepy little channel continue its journey. And to those of you already subscribed, thank you. Your support means more than you know. Tonight, we're going to wander through something quite extraordinary. We're going to explore mathematical problems so stubborn, so beautifully resistant to solution, that they've captivated the greatest minds across centuries. These aren't just equations scribbled on a blackboard and forgotten. These are problems that have haunted mathematicians through generations. Problems that have sparked obsessions, driven people to the edge of their sanity, and occasionally, after hundreds of years, finally revealed their secrets. What makes an equation take centuries to solve? Is it the complexity of the mathematics involved? Is it that we simply don't have the right tools yet? Or is it something more mysterious? Something about the nature of truth itself that makes certain mathematical statements resist proof for generation after generation. Tonight, you'll meet a French mathematician who scribbled a note in the margin of a book, claiming he had discovered something marvelous, something too large to fit in the narrow space available. That margin note would taunt the mathematical world for 358 years. You'll encounter problems so simple that a child could understand them, yet so profound that even the most brilliant mathematicians of our time freely admit they have no idea how to solve them. And you'll discover that sometimes the journey to solve these problems creates entirely new branches of mathematics, new ways of thinking that prove even more valuable than the answer itself. So settle in. Let your breathing slow. There's no rush tonight. We have centuries to explore, mysteries to unravel gently, and stories that wind through the lives of people who dedicated everything to understanding just one more piece of the infinite puzzle that is mathematics. Let's begin with perhaps the most famous mathematical mystery of all time, a problem that started with a margin note and ended with tears of joy in a Cambridge lecture hall 3.5 centuries later. Picture this. It's the year 1637. Somewhere in France, a lawyer and amateur mathematician named Pierre de Fermat is reading his copy of an ancient Greek text called Arithmetica by Diophantus. The book is about number theory, the study of whole numbers and their properties, and Fermat is fascinated. As he reads, he scribbles notes in the margins. Some are simple observations, others are more profound. But then, next to a problem about writing squares as sums of other squares, Fermat writes something that will echo through the centuries. He writes, and I'm translating from the Latin, "It is impossible for a cube to be the sum of two cubes, a fourth power to be the sum of two fourth powers, or in general, for any number that is a power greater than the second to be the sum of two like powers." And then, tantalizingly, maddeningly, he adds, "I have discovered a truly marvelous demonstration of this proposition, which this margin is too narrow to contain." Let's pause here and let that sink in gently. Fermat claimed he could prove something. He said he had the proof, but the margin was too small to write it down. And then he never wrote it anywhere else. Or if he did, that piece of paper was lost to history. What Fermat was claiming sounds simple enough. Everyone who studied basic math knows about the Pythagorean theorem. 3 squared plus 4 squared equals 5 squared. 9 plus 16 equals 25. You can find whole number solutions to the equation x squared plus y squared equals z squared. There are infinitely many of these solutions, called Pythagorean triples. But Fermat was saying that if you change that little exponent from 2 to anything bigger, 3, 4, 5, a million, it becomes impossible. You cannot find 3 whole numbers where x cubed plus y cubed equals z cubed. You cannot find 3 whole numbers where x to the 4th plus y to the 4th equals z to the 4th, and so on, forever, for every power greater than 2. This statement became known as Fermat's last theorem. Not because it was the last theorem Fermat ever stated, but because it was the last of his claims to be proven or disproven. All his other mathematical statements were eventually verified or shown to be wrong. But this one resisted every attempt. Fermat himself had actually proved the case for fourth powers. He showed that you cannot write a fourth power as the sum of 2 fourth powers. So mathematicians knew he understood at least part of the problem. But the general case for all powers greater than 2, that remained a mystery wrapped in the most tantalizing of clues, a margin note claiming a proof too marvelous to fit. Did Fermat really have a proof? Most mathematicians today think probably not. The tools required to ultimately prove the theorem wouldn't be invented for another 300 years. But we'll never know for certain what Fermat thought he had discovered. All we know is that he started a quest that would consume generations of the world's greatest mathematical minds. For decades after Fermat's death in 1665, mathematicians tried to find his lost proof, or to prove the theorem themselves, or perhaps to find a counterexample, 3 numbers that would show Fermat was wrong. The search began immediately. Fermat's son, Samuel, published his father's annotated copy of Arithmetica in 1670, just 5 years after Pierre's death. The margin notes became public knowledge, and mathematicians across Europe began to puzzle over them. Most of Fermat's claims were proven relatively quickly, but that one theorem, the one about powers greater than 2, stubbornly resisted. They started with specific cases. If you can't prove it for all powers, maybe you can prove it for specific powers. This strategy makes sense. Mathematics often works this way. You tackle the simpler cases first, hoping to find a pattern or technique that will generalize to all cases. Fermat himself had proved the case for fourth powers. His proof used a technique he invented called infinite descent. The idea is beautifully clever. You assume a solution exists, then show that if it does, there must be a smaller solution. And if there's a smaller solution, there must be an even smaller one, and so on, forever. But you can't have an infinite descending sequence of positive whole numbers. Eventually, you'd reach 0, or negative numbers. This contradiction means your initial assumption must be wrong. No solution exists. Fermat's infinite descent proof for the fourth power case gave mathematicians hope. If he could do it for 4, Surely the technique could be extended to other powers. But it wasn't that simple. The infinite descent argument that works for 4 doesn't directly translate to other exponents. In 1770, over a century after Fermat's death, Leonhard Euler finally proved the case for cubes. Euler was one of the most prolific mathematicians in history. His collected works fill more than 70 volumes. He made fundamental contributions to calculus, graph theory, topology, number theory, and countless other fields. He even continued doing mathematics after going blind in his later years, dictating his results to assistants. Euler's proof for cubes used a modified form of Fermat's infinite descent. But with additional algebraic cleverness, he showed that if you could write a cube as the sum of 2 cubes, you could manipulate the equation to produce a smaller solution, leading to the same contradiction. It was a triumph, but it was also sobering. If it took a mathematician of Euler's caliber over 100 years to prove just one more case, how long would it take to prove all cases? Progress was painfully slow. By 1839, over 2 centuries after Fermat's margin note, mathematicians had managed to prove the theorem for exactly 3 prime number exponents: 3, 5, and 7. Let me emphasize that again. 202 years, multiple generations of mathematicians, 3 cases proven. The case for exponent 5 was proved by independent work of Adrien-Marie Legendre and Peter Gustave Lejeune Dirichlet around 1825. The case for 7 was proved by Gabriel Lamé in 1839. Each proof was harder than the last. Each required new insights and techniques. And with each success, it became clear that a general proof, one that would work for all exponents simultaneously, was nowhere in sight. But during this long struggle, something beautiful happened. A brilliant mathematician named Sophie Germain developed new approaches to the problem. And the fact that she accomplished this at all is remarkable, because Sophie Germain faced obstacles that had nothing to do with mathematics. Germain was born in Paris in 1776, on April 1st. She grew up during one of the most turbulent periods in French history. She was 13 when the Bastille was stormed, marking the beginning of the French Revolution. As a child, confined to her home during the violence and chaos outside, she discovered her father's library and began reading mathematics books. Her parents were alarmed. Mathematics was not considered appropriate for young women. They confiscated her candles and took away her warm clothing, trying to discourage her late-night studying. But Germain was determined. She studied by the light of hidden candles, wrapped in blankets she'd secreted away, teaching herself Latin and Greek so she could read the mathematical classics in their original languages. When the École Polytechnique opened in Paris in 1794, Germain was 18. She desperately wanted to attend, but the school didn't admit women, so she obtained lecture notes from courses under the name of a former student, Monsieur Antoine Auguste Leblanc. She began submitting papers using this male pseudonym. Her work caught the attention of Joseph Louis Lagrange, one of the professors and one of the greatest mathematicians of the era. Lagrange was so impressed by Leblanc's submissions that he asked to meet the brilliant young man. When Germain revealed her true identity, Lagrange was astonished, but to his credit, he became one of her supporters and mentors. Germain would go on to make important contributions to several areas of mathematics and physics. But her work on Fermat's last theorem was perhaps her most significant achievement. She developed what became known as Sophie-Germain's theorem, a result that proved Fermat's last theorem for an entire class of prime numbers. Her approach was ingenious. She worked with what are now called Sophie-Germain primes, prime numbers p, where 2p plus 1 is also prime. For these special primes, she was able to prove the first case of Fermat's last theorem, which deals with situations where the exponent doesn't divide any of x, y, or z. This was a major breakthrough. Rather than proving the theorem one exponent at a time, she'd proven it for infinitely many exponents all at once. Germain's work influenced mathematicians for decades. Her ideas were refined and extended by others, pushing the boundaries of what had been proven. But even with her brilliant contributions, the complete theorem remained tantalizingly out of reach. Germain's life was not easy. She worked in isolation. Without the support of an academic institution, she corresponded with other mathematicians, but always with the awareness that her gender made her an outsider. When she submitted a paper on the mathematical theory of elasticity to the French Academy of Sciences, a paper that would eventually win a prize, the judges noted that while the work was excellent, it was a shame it hadn't been more rigorously written, perhaps because one judge suggested the author was merely a woman. Despite everything, Germain persisted. She continued working on mathematics until her death from breast cancer in 1831 at the age of 55. On her death certificate, her occupation was listed as property holder, not mathematician. But history remembers her differently. Today, several mathematical concepts bear her name, and she's recognized as one of the pioneers of number theory. Think about that gently for a moment. Here was a problem stated in 1637. Here was a woman born in 1776, 140 years later, teaching herself mathematics in secret and making progress on a problem that had stumped the greatest minds of Europe. The problem had already been unsolved for longer than most people lived, and yet she found new approaches, new insights, new ways forward. And yet, even with Germain's contributions, even with the work of Euler and Legendre and Dirichlet and Lamé and all the others, the complete proof remained out of reach. The theorem continued to resist. Decades turned into centuries. The 1800s gave way to the 1900s, and still, Fermat's last theorem stood unsolved. Let's drift forward now to the middle of the 1800s. A German mathematician named Ernst Kummer became fascinated with Fermat's last theorem. Kummer was born in 1810 in Sorau, Prussia. He was a patient, systematic thinker, the kind of mathematician who would spend years developing the right tools before attacking a problem. By the time Kummer began his work, Fermat's last theorem had been unsolved for over 2 centuries. The proven cases remained stuck at just a handful of specific exponents. It was becoming clear that the techniques used so far, variations on Fermat's infinite descent, and clever algebraic manipulations, wouldn't be sufficient for a general proof. Something fundamentally new was needed. Kummer realized that to make progress, he needed to venture into a relatively new area of mathematics called algebraic number theory. This field extends beyond the ordinary whole numbers that we learn about in elementary school. It explores more exotic mathematical objects, complex numbers, algebraic integers, and other strange mathematical creatures. Let me paint a picture of what Kuma was doing, though we'll keep it gentle and conceptual rather than technical. Imagine you're trying to solve a puzzle, but the pieces don't quite fit together properly. Maybe there are gaps or pieces that should connect but don't quite line up. One approach would be to keep trying with the pieces you have. Another approach, Kuma's approach, was to create new pieces, pieces that existed in a sort of extended puzzle space. That's what algebraic number theory does. It creates new mathematical objects that fill in the gaps, that make connections that seemed impossible before. But here's the fascinating part. These new objects follow their own rules. They behave differently than ordinary numbers. And understanding those rules, developing the theory of how these exotic mathematical objects work, that became Kuma's life's work. In doing so, Kuma essentially created a new branch of mathematics, the theory of ideals, a fundamental concept in modern algebra that every mathematics graduate student learns today, was developed in large part because of attempts to prove Fermat's last theorem. Kuma introduced ideals as a way to restore certain properties that ordinary numbers have, but that his exotic algebraic integers seem to lack. This pattern, where the pursuit of one problem generates entirely new mathematics, is one of the recurring themes in our story tonight. Mathematics doesn't just move forward by solving problems. It moves forward by developing new tools, new concepts, new ways of thinking. And these tools often turn out to be useful, far beyond the original problem that inspired them. Through years of painstaking work, Kuma managed to prove Fermat's last theorem for what he called regular primes. Without getting too deep into the technical details, let's just say he showed the theorem was true for a large class of cases. He established criteria for deciding whether a given prime number was regular or irregular. For the regular primes, he had a proof that Fermat's last theorem held. This was enormous progress. Kuma had proven the theorem for infinitely many cases at once, not just 3 or 7 or 11, but infinitely many primes, all the regular ones. It was like going from checking individual puzzle pieces to verifying entire sections of the puzzle simultaneously. But not all cases. There remained the irregular primes, special troublesome cases that resisted his methods. These irregular primes are relatively rare, appearing about 39% of the time among all primes. The first few irregular primes are 37, 59, and 67. For these cases, Kuma's elegant theory didn't immediately apply. Each irregular prime needed to be handled individually, with special arguments tailored to that specific case. Still, Kuma's work was groundbreaking. It opened new avenues of research. Other mathematicians could now build on his foundation, extending his results, handling the irregular primes one by one. And that's exactly what happened. By the late 1800s, using Kuma's techniques and the techniques of others building on his work, mathematicians had verified Fermat's last theorem for all exponents up to 100. Then, as mathematical methods improved and as early computing devices became available, they pushed further. By the early 1900s, the theorem had been verified up to several thousand. By mid-century, up to hundreds of thousands. In 1954, two mathematicians named Harry Vandiver and D.H. Lehmer used one of the early electronic computers to verify Fermat's last theorem for all exponents up to 2053. This was a significant achievement, showing how computation could accelerate mathematical verification. But even as computers became more powerful, even as the verified cases climbed into the millions and then billions, mathematicians knew this wasn't a proof. Here's the thing about infinity. You can verify a statement for 1 billion cases, and you're still no closer to proving it's true for all cases. You could verify it for 1 trillion cases, and there would still be infinitely many cases left unchecked. This is what makes number theory both beautiful and frustrating. A single counter-example could lurk out there at some unimaginably large number, and you'd never find it by just checking cases one by one. The verification was useful, though. Each failed attempt to find a counter-example increased mathematicians' confidence that Fermat was right. The theorem seemed to be true, but seeming true and being proven true are very different things in mathematics. A theorem, by definition, requires a proof. Without one, you just have a conjecture, no matter how plausible. By the turn of the 20th century, Fermat's last theorem had been unsolved for over 260 years. It had become the most famous unsolved problem in mathematics. Every mathematician knew about it. Many had tried their hand at it. None had succeeded in finding a general proof. In 1900, at the Second International Congress of Mathematicians held in Paris, the great mathematician David Hilbert presented a list of 23 unsolved problems that he believed would drive mathematical progress in the coming century. This list, known as Hilbert's Problems, became famous. Working on a Hilbert problem meant working on something important, something at the frontier of mathematics. Fermat's last theorem was so famous it didn't even need to be on Hilbert's list. Everyone already knew about it. It had transcended being just another unsolved problem. It had become a cultural touchstone, the unsolved problem, the mathematical equivalent of the Holy Grail. Around this time, in 1908, a wealthy German industrialist and amateur mathematician named Paul Wolfskehl established a prize for whoever could prove Fermat's last theorem. The prize was 100,000 German marks, a substantial fortune at the time. Wolfskehl died shortly after establishing the prize, and it was to be awarded from his estate. There's a legend about why Wolfskehl established this prize. A story that may or may not be true, but that captures something important about the relationship between mathematics and human life. The story goes that Wolfskehl had been deeply depressed and had decided to commit suicide. He set midnight as the time. Everything was prepared. He had written his will, put his affairs in order, and was waiting for the appointed hour. But as midnight approached, he found himself with some time to kill, and he picked up a mathematical paper. It was about Fermat's last theorem, discussing some recent work by Kummer. Wolfskehl began reading. He became absorbed in following the mathematical arguments. He started working through the proofs himself, checking the logic, seeing where things connected. Time passed. Midnight came and went, unnoticed. Hours went by. When Wolfskehl finally looked up from his mathematical work, dawn was breaking. The night had passed, and something in him had changed. The despair that had driven him towards suicide had lifted. Mathematics had saved his life. In gratitude, he decided to establish the prize for solving the problem that had captured his attention during those crucial hours. Is this story true? We don't know for certain. The details are disputed, and some historians think it's apocryphal. But true or not, it illustrates something real: the power of mathematics to captivate, to draw you out of yourself, to make you forget everything else in the pure joy of understanding. The Wolfscale Prize made Fermat's last theorem even more famous. Now, there wasn't just intellectual glory at stake. There was money. Over the years, thousands, perhaps tens of thousands of purported proofs were submitted. Professional mathematicians, amateur enthusiasts, cranks and dreamers all tried their hand. The vast majority of these submissions were obviously wrong. They made elementary errors, misused mathematical concepts, or simply didn't understand what constituted a valid proof. But sorting through them all was a burden. The prize committee, tasked with evaluating submissions, had to examine each one carefully enough to determine if it might be valid. And sometimes, submissions from respected mathematicians had to be carefully analyzed. These proofs would be sophisticated, using advanced mathematics, and it would take experts weeks or months to find the subtle error that invalidated them. Every single proof, without exception, contained errors. The problem remained unsolved. The early 20th century saw continued progress on Fermat's last theorem, but it was incremental. New techniques from algebraic number theory were applied. The class field theory developed by mathematicians like Teiji Takagi and Emil Artin provided powerful new tools. Computational verification continued to push forward, with the theorem verified for larger and larger exponents. But the general proof remained out of reach. As the 1900s progressed, as we passed the 250th anniversary of Fermat's margin note, then the 300th anniversary, some mathematicians began to wonder if the problem was simply too hard. Maybe it would never be solved. Maybe Fermat's last theorem would join the ranks of those mathematical statements that are true but unprovable. And then, in 1963, something happened that would set the stage for everything that followed. A 10-year-old boy in England borrowed a book from his local library. Andrew Wiles was that 10-year-old boy, and the book was The Last Problem by E.T. Bell. The book told the story of Fermat's last theorem, this centuries-old problem that had defeated the greatest mathematicians in history. Bell's book was romantic, dramatic, painting mathematics as an adventure filled with heroes and villains, triumphs and tragedies. Young Andrew Wiles, growing up in Cambridge, England, was exactly the right age to be captivated by such a story. 10 years old is that magical age when you're old enough to understand complex ideas, but young enough to believe that anything is possible. Your life stretches out before you, infinite with potential. The future is a blank canvas. Wiles was captivated. Here was a problem that anyone could understand. The statement of Fermat's last theorem requires no advanced mathematics. A bright middle school student could grasp what it's asking. There are no complex formulas to memorize, no intricate diagrams to interpret, just a simple statement. You cannot write a power greater than 2 as the sum of two like powers. And yet it had remained unsolved for over 300 years. The young Wiles made a promise to himself the kind of promise that children make with absolute seriousness, not yet understanding the magnitude of what they're committing to. Someday, somehow, he would solve Fermat's last theorem. He would be the one to finally answer Fermat's challenge. He would find the marvelous proof that Fermat claimed was too large for the margin. Now, imagine the audacity of that dream. Imagine being 10 years old and deciding you're going to solve a problem that has defeated 3 centuries of brilliant mathematicians. Euler had tried, Legendre had tried, Kummer had tried. Sophie Germain had made significant progress but hadn't solved it. Hilbert had considered it important enough to hover around his famous list of problems. And all of them, every single one, had fallen short of a complete proof. It's the mathematical equivalent of a child saying, "I'm going to climb Mount Everest," except perhaps even more ambitious. At least Mount Everest had been climbed before. Edmund Hillary and Tenzing Norgay had reached the summit in 1953. But Fermat's last theorem, nobody had reached that summit. It stood there, pristine and unconquered, challenging generations. But Wiles held on to his dream. As he grew older, as he progressed through school, he kept that promise in the back of his mind. He was good at mathematics, very good. He excelled in his classes, won academic prizes, and eventually earned a place at Oxford University to study mathematics at the undergraduate level. At Oxford, Wiles studied under the guidance of some excellent mathematicians. He learned the formal language of proofs, the techniques of algebraic number theory, the deep structures underlying the simple arithmetic he had learned as a child. Mathematics at the university level is very different from school mathematics. It's not about calculating answers or memorizing formulas. It's about understanding structures, patterns, connections. It's about seeing the architecture underneath the surface. After Oxford, Wiles moved to Cambridge University for his doctoral work. Cambridge has one of the great mathematical traditions. Newton had worked there. Hardy and Littlewood, Ramanujan's collaborators, had been there. The Cavendish Laboratory, where so much physics was discovered, was there. The Isaac Newton Institute, where Wiles would eventually announce his proof, was there. It's a place saturated with mathematical history. Wiles completed his PhD in 1980 under the supervision of John Coates. His thesis was on elliptic curves, which would prove to be prophetic, though he didn't know it at the time. He was building expertise in exactly the areas that would eventually be needed for Fermat's last theorem. After completing his doctorate, Wiles took a position at Princeton University in New Jersey. Princeton, like Cambridge, has an extraordinary mathematical pedigree. Einstein had been there. Gödel had been there. John von Neumann, one of the most brilliant mathematicians of the 20th century, had been there. It was, and remains, one of the great centers of mathematical research in the world. At Princeton, Wiles worked in number theory, the branch of mathematics most relevant to Fermat's last theorem. He published papers, attended conferences, collaborated with other mathematicians. He built a reputation as an excellent mathematician, someone doing solid, important work. He was becoming established in his field. But for years, he didn't actively work on Fermat's last theorem itself. As he would later explain, Fermat's last theorem was considered a career killer in mathematics. It was too hard. Too many smart people had wasted years on it, or even decades, with nothing to show for their efforts. any young mathematician who focused on it would likely produce nothing, and their career would stall. In academic mathematics, career advancement depends on publications. You need to prove new theorems, write papers, get them published in respected journals. If you spend years working on a problem and produce nothing, you might not get tenure. You might not get grants. You might not be taken seriously by your colleagues. It's a risk, and Fermat's last theorem was seen as the ultimate risky problem. It had a graveyard full of failed attempts. Brilliant mathematicians had dedicated significant portions of their careers to it and achieved nothing. It had a reputation as an attractive nuisance, something that looked solvable but wasn't, something that could seduce you into wasting your prime research years. So Wiles was careful. He worked on other problems, important problems in number theory and algebraic geometry. He published regularly. He built his career on solid ground. He got tenure at Princeton, a position of security and prestige. He married, started a family. His life had structure and success. But Fermat's last theorem was always there, in the back of his mind, like a low hum he could never quite forget. The 10-year-old's promise hadn't been forgotten. It had just been deferred, waiting for the right moment. And then, in 1986, everything changed. Another mathematician named Ken Ribet proved something remarkable, something that suddenly made Fermat's last theorem seem potentially solvable for the first time in centuries. To understand what Ribet proved, we need to talk about two completely different areas of mathematics: elliptic curves and modular forms. These might sound intimidating, but let's approach them gently, without worrying too much about the technical details. We're more interested in the story, the connections, the human element of discovery. Elliptic curves are, despite their name, not ellipses. They're not even curves in the usual sense. They're mathematical objects defined by certain types of equations, equations involving squares and cubes of variables. A typical elliptic curve might be defined by an equation like y squared equals x cubed minus x plus 1. If you plot all the points that satisfy this equation on a graph, you get a shape that loops around in an interesting way. But mathematicians don't care about elliptic curves primarily for their shapes. They care about them because of their algebraic properties. Elliptic curves have a beautiful, symmetric internal structure. You can define an addition operation on the points of an elliptic curve in a natural way, and this addition gives the points a group structure, one of the fundamental concepts in abstract algebra. Mathematicians had studied elliptic curves for centuries, long before they were called elliptic curves. They appear in ancient problems about Pythagorean triples. They appear in attempts to calculate the arc length of an ellipse, which is where the name elliptic comes from, even though the curves themselves aren't ellipse. By the 20th century, elliptic curves had become central objects in algebraic geometry and number theory. They're connected to deep questions about the nature of numbers and geometric structures. Now, let's shift to a completely different part of mathematics: modular forms. If elliptic curves require some imagination to visualize, modular forms are even more abstract. They're special types of functions, functions that take complex numbers as input and produce complex numbers as output, but not just any functions. Modular forms have an extraordinary amount of symmetry. To really understand modular forms, requires complex analysis, abstract algebra, and several other advanced mathematical fields. But here's the key point for our story. Modular forms are defined by their symmetries. They remain unchanged under certain transformations of their input. They have a regularity, a predictability, a highly structured nature. These symmetries make modular forms incredibly useful in number theory. They appear in the study of prime numbers, in partition problems, in questions about representing numbers as sums of squares. The famous mathematician Srinivasa Ramanujan, working in the early 20th century, discovered deep and mysterious formulas involving modular forms, formulas that continue to inspire mathematicians today. So we have elliptic curves on one side, studied by algebraic geometers and arithmetic geometers, objects with rich algebraic structure. And we have modular forms on the other side, studied by analysts and number theorists, functions with extraordinary symmetry. These two areas of mathematics seem to have nothing to do with each other. They came from different historical traditions. They used different techniques. The mathematicians working on them often didn't talk to each other. Elliptic curves and modular forms come from completely different parts of the mathematical landscape. It's like comparing poetry and architecture. Both might be forms of human expression. Both might have aesthetic value, but they operate in different mediums with different rules, serving different purposes. Or do they? In the 1950s, two Japanese mathematicians, Yutaka Taniyama and Goro Shimura, began to suspect there might be a deep connection. They were young mathematicians, not yet established, working in Tokyo. And they had a bold, almost crazy idea. They conjectured, that is, they proposed without proof, that every elliptic curve could be associated with a modular form. Every single elliptic curve, they claimed, corresponds to some modular form. The two worlds weren't separate after all. They were different views of the same underlying mathematical reality. This was called the Taniyama-Shimura conjecture. And when it was first proposed, most mathematicians thought it was too good to be true. It was claiming that two entirely different mathematical worlds were secretly the same world. It was like discovering that poetry and architecture were actually the same thing viewed from different angles, that sonnets and cathedrals were built from the same fundamental blueprints. The mathematical communities studying elliptic curves and those studying modular forms operated almost independently. They had their own conferences, their own journals, their own traditions. The Taniyama-Shimura conjecture said they'd been studying different aspects of the same underlying reality all along. If true, it would be one of the most profound connections in all of mathematics. Most mathematicians were skeptical. The conjecture seemed too beautiful, too elegant. Mathematics is full of beautiful conjectures that turn out to be false. You can't just assume that because something would be nice if it were true, it actually is true. You need proof. And nobody had any idea how to prove the Taniyama-Shimura conjecture. It seemed completely out of reach. Tragically, Yutaka Taniyama didn't live to see the later developments. He died by suicide in 1958, at the age of 31. His death was a tremendous loss to mathematics. Who knows what he might have discovered had he lived longer. Goro Shimura continued working on the conjecture and related questions for decades, eventually moving to Princeton University, where he would be a colleague of Andrew Wiles. Through the 1960s and 70s, more mathematicians began to take the Taniyama-Shimura conjecture seriously. André Weil, one of the great mathematicians of the 20th century, contributed to refining and extending the conjecture. It began to be called the Taniyama-Shimura-Weil conjecture in recognition of Weil's contributions. Evidence accumulated, special cases were proven, connections to other parts of mathematics were discovered, but a general proof remained elusive. The conjecture was considered one of the most important unproven statements in mathematics. If it were true, it would have profound implications for number theory and many other fields, but proving it seemed impossibly difficult. And then, in 1984, a mathematician named Gerhard Frey had a remarkable insight. Frey was a German mathematician working at the University of Saarland. He was thinking about elliptic curves and about Fermat's last theorem, and he realized something extraordinary. He realized that if Fermat's last theorem were false, if you could find whole numbers x, y, and z, such that x to the n plus y to the n equals z to the n for some n greater than 2, then you could use those numbers to construct a very weird elliptic curve. You could take the Fermat equation and transform it into an elliptic curve with strange, almost pathological properties. This hypothetical elliptic curve, now called a Frey curve, would be so weird that it probably couldn't be modular. It would violate certain conditions that modular elliptic curves had to satisfy. In other words, if Fermat's last theorem were false, you could construct an elliptic curve that wasn't modular. Do you see where this is going? Let's walk through the logic slowly, gently, because this is the key insight that would eventually lead to the proof. If the Taniyama-Shimura conjecture was true, then every elliptic curve had to be modular. Every single one, without exception. But if Fermat's last theorem was false, you'd get an elliptic curve, the Frey curve, that wasn't modular. These two statements contradict each other. They can't both be true. Therefore, if you could prove that every elliptic curve is modular, if you could prove the Taniyama-Shimura conjecture, then Fermat's last theorem would have to be true. Because if it were false, you'd have a contradiction. You'd have an elliptic curve that both was and wasn't modular, which is impossible. This was Frey's brilliant insight. He saw a connection between two seemingly unrelated problems. But there was a gap in the logic. Frey had shown the connection intuitively, but he hadn't proven it rigorously. His Frey curve was suspicious, but was it definitely not modular? That needed proof. This is where Ken Ribet enters our story. Ribet was an American mathematician at the University of California, Berkeley. He was an expert in exactly the areas needed to make Frey's intuition rigorous. In 1986, Ribet succeeded in proving what became known as Ribet's theorem, or sometimes the epsilon conjecture. Ribet showed rigorously that Frey's insight was correct. He proved that if you could construct a Frey curve from a solution to Fermat's equation, that curve could not be modular. The logic was now ironclad. The Taniyama-Shimura conjecture implied Fermat's last theorem. When Ribet's proof was announced, Andrew Wiles was in his office at Princeton. He heard the news, and he felt something shift inside him. After decades of dormancy, his childhood dream roared back to life. He now had a path forward. If he could prove the Taniyama-Shimura conjecture, or at least the part of it needed for Frey's curve, he would prove Fermat's last theorem. There was just one small problem. though calling it small would be quite an understatement. The Taniyama-Shimura conjecture was considered one of the most difficult, unproven statements in mathematics. It had been open for over 30 years. Most experts thought it was completely out of reach with current techniques. Some thought it might take a century to prove. Some thought it might never be proven at all. Many mathematicians, hearing about Ribet's result, thought it was more of a curiosity than a real pathway to solving Fermat's last theorem. Sure, the two problems were now connected, but since both seemed impossibly hard, connecting them didn't really help. It was like saying that if you could fly to the moon, you could probably fly to Mars. True, perhaps, but not helpful if you can't fly to the moon. But Andrew Wiles didn't care about the conventional wisdom. He didn't care that experts thought it was impossible. He had made a promise to himself as a 10-year-old boy. And now, for the first time, he saw a genuine mathematical path forward. It might be incredibly difficult. It might take years. It might ultimately prove impossible. But it was a path, and Wiles decided to walk it. More than that, he decided to walk it alone, in secret, hidden from the mathematical world. In 1986, Andrew Wiles made an extraordinary decision, one that went against almost everything about how modern mathematics is conducted. He would work on the Taniyama-Shimura conjecture in complete secrecy. He told almost no one what he was doing. He stopped publishing papers on other topics. He stopped going to most conferences. He stopped collaborating with other mathematicians. He essentially went dark, mathematically speaking. This is almost unheard of in modern mathematics. Today's mathematics is a collaborative enterprise. Mathematicians work in teams, share partial results, give talks about work in progress, circulate preprints of papers before publication. This collaboration is essential. Mathematics has become so specialized, so complex, that no one person can master everything. You need to talk to experts in other areas. You need feedback on your ideas. You need to know what others are discovering so you don't duplicate work or miss important connections. But Wiles knew that announcing he was working on the Taniyama-Shimura conjecture and, by extension, Fermat's last theorem, would create enormous pressure. Every few months, people would ask him how it was going. If years passed without results, they would assume he'd failed. They might even think his judgment was poor, that he'd wasted his career on an impossible problem. And worse, if he shared partial results, someone else might use his ideas to solve it first, or claim credit for contributions that were really his. So Wiles made the decision to work alone. For 7 years, from 1986 to 1993, he pursued the proof in secret. He went to his office at Princeton. He went home to his family. And in between, in the quiet hours, in the solitude of his study, he attacked the problem. His wife, Nada, knew he was working on something important, but even she didn't know all the details. His daughters knew. Daddy spent a lot of time thinking about mathematics. His colleagues at Princeton wondered where Wiles had gone. He'd been a regular presence at seminars and colloquia, always interested in hearing about new results, always willing to discuss ideas. But now he was absent. He attended only the minimum necessary departmental meetings. He taught his classes, but didn't linger to chat with students afterward. He was pulling away from the community. Some colleagues worried. Was something wrong? Was he having personal problems? Was his marriage in trouble? Had he lost interest in mathematics? It's not uncommon for mathematicians to burn out, to reach a point where the constant pressure to produce new results becomes too much. Was that happening to Wiles? But Wiles was fine, more than fine. He was engaged in the most intense, focused period of mathematical work of his life. Every day, he would make progress on some small piece of the puzzle, or he would hit a wall and need to backtrack, trying a different approach, or he would realize that a path he'd been following for months was a dead end, and he'd need to start over on that piece of the problem. He couldn't prove the entire Taniyama-Shimura conjecture. That was far too vast. The conjecture applies to all elliptic curves, an infinite variety of objects with different properties. But he didn't need to prove it for all elliptic curves. He could focus on a special case, a subset of elliptic curves called semi-stable elliptic curves. If he could prove that all semi-stable elliptic curves were modular, that would be enough. Frey's weird curve, the one constructed from a hypothetical solution to Fermat's equation, would fall into this category. Semi-stable elliptic curves are those that have a certain nice behavior when you look at them from different mathematical perspectives, what mathematicians call different primes. They're better behaved than elliptic curves in general, though still extraordinarily complex objects. Even this restricted problem was formidable. The mathematics Wiles needed was forbidding, drawing from multiple advanced fields. He had to master techniques from algebraic geometry, the study of geometric objects defined by polynomial equations. He needed algebraic number theory, which extends ordinary arithmetic to more exotic number systems. He needed representation theory, which studies how algebraic objects can be represented by matrices and transformations. He needed to understand Galois representations, which connect number theory to group theory in subtle ways. Each of these areas is a lifetime of study for most mathematicians. Wiles needed to become expert enough in all of them to see connections, to adapt techniques, to forge new paths where none existed. And he had to do it largely alone. His typical day would start with breakfast with his family, getting his daughters ready for school, the normal routines of domestic life. Then he'd head to his office at Princeton. He'd close the door and start thinking. Sometimes he'd write, covering pages with calculations and diagrams. Sometimes he'd just sit and think, staring at the wall or out the window, working through ideas in his head. He described it later as being like exploring a dark mansion. You enter a vast, shadowy house. You can't see anything. You grope around in the darkness, bumping into furniture, trying to figure out where you are. Occasionally, you find a light switch, and a room illuminates. You see what's there, understand that piece of the structure. But then, you move on to the next dark room, and you're blind again. Most of the time, Wiles said, you're stumbling in the dark. You try something, and it doesn't work. You try something else, and it doesn't work either. You might spend days or weeks on an approach that ultimately leads nowhere. And you have to have faith, even when you can't see anything, that there's a way through. That if you keep searching, keep trying, eventually you'll find the path. The isolation was both necessary and difficult. Necessary because he needed to avoid the pressure and distractions that would come from announcing his work. Difficult because he had no one to talk to, no one to check his reasoning, no one to suggest alternative approaches when he got stuck. He was entirely alone with one of the hardest problems in mathematics. There were dark periods, times when he felt lost, when nothing seemed to work, when he wondered if he was wasting his time. After a year of work, he might look back and realize he'd made very little tangible progress. After 2 years, he might feel he was still nowhere near a proof. The goal seemed impossibly distant, but he kept going, day after day, month after month, year after year. 1986 became 1987, then 88, 89, 90. He was now in his late 30s, then his 40s. His daughters were growing up. The world was changing. The Soviet Union collapsed. The Cold War ended. The internet was emerging. And Andrew Wiles sat in his office, working on a problem first stated in 1637. His wife said there were times when she'd find him staring into space at the breakfast table, barely present, his mind deep in some intricate web of mathematical ideas. She'd have to repeat herself to get his attention. His colleagues began to wonder if something was seriously wrong. Had he given up on research? Was he having personal problems? Had he lost his passion for mathematics? But Wiles was more passionate than ever. He was driven by something beyond ordinary professional ambition. This wasn't about getting tenure or winning awards or impressing his colleagues. This was about that promise he'd made to himself as a 10-year-old boy. This was about finally answering a question that had haunted him for most of his life. By 1992, Wiles felt he was close. He had assembled most of the pieces of the proof. The architecture of the argument was in place. But there were still gaps, places where the logic didn't quite connect, technical difficulties that needed to be overcome. He worked through these one by one, painstakingly filling in the details. And then, in early 1993, after nearly 7 years of solitary work, Wiles believed he had it. He had proved that all semi-stable elliptic curves were modular, which meant that Frey's curve couldn't exist, which meant that Fermat's last theorem was true. After 358 years, the problem was solved. But how to announce it? Wiles couldn't just post a preprint and wait for people to read it. This was too important. And after 7 years of silence, he needed to explain not just the proof, but the journey that led to it, the techniques he'd developed, the connections he'd found. He decided to give a series of lectures at Cambridge University, his old graduate school. The title would be vague, not giving away the punchline. Modular forms, elliptic curves, and Galois representations. But word would spread. Mathematicians would suspect something big was coming, and then, at the right moment, he would reveal what he'd been working on all these years. The lectures were scheduled for June 1993. The Isaac Newton Institute for Mathematical Sciences at Cambridge would host them. And Andrew Wiles, after 7 years in the wilderness, was about to step back into the light. June 23rd, 1993. The lecture hall at the Isaac Newton Institute in Cambridge is packed. Mathematicians from around the world have travelled to be there. They sense something historic is about to happen. Wiles begins his lecture. He moves through the material calmly, methodically. He's explaining how various mathematical pieces fit together. The audience is following along, impressed by the elegant mathematics, but not yet sure where it's heading. Then, near the end of his third lecture, Wiles writes on the board, a corollary of everything he's just presented. He writes, "This implies Fermat's last theorem." The room erupts. Applause, gasps. Some mathematicians are in tears. After 358 years, Fermat's last theorem has been proven. The longest-standing problem in mathematics has fallen. Wiles simply says, "I think I'll stop here." The news spreads rapidly. The New York Times puts it on the front page. It's rare for pure mathematics to make mainstream news, but this is special. Everyone has heard of Fermat's last theorem. Everyone knows it's been unsolved for centuries. And now, finally, there's an answer. But then, a few months later, disaster. Mathematicians began examining Wiles's proof in detail. The proof was long, over 200 pages, using sophisticated mathematics from multiple fields. It would take time to verify, but that was normal for important proofs. And then someone found a gap. In one section of the proof, Wiles had used a mathematical technique that didn't quite work the way he needed it to. The logic had a hole. Was the entire proof wrong? Could the gap be fixed? Or had Wiles, like so many before him, come tantalizingly close only to fall short? Wiles was devastated. He'd spent 7 years in isolation, building this proof. He'd announced it to the world, and now it seemed it might all crumble. He brought in a former student of his, Richard Taylor, to help. Together, they worked to fix the gap. They tried one approach, then another. Months passed. The mathematical community waited anxiously. Some began to write obituaries for the proof, assuming it couldn't be saved. Wiles later described this as the darkest period of his mathematical life. He'd come so close. He'd been so sure. And now he was struggling in public view, with the whole world watching. On September 19th, 1994, Wiles had a sudden realization. He saw how two different approaches he'd been considering could be combined. One approach had a weakness in exactly the place where the other was strong. If he merged them, the gap in the proof could be filled. He worked through the details with Taylor. It worked. The proof was complete. In 1995, Wiles and Taylor published their work. The mathematical community reviewed it thoroughly. This time, it held. The proof was correct. Fermat's last theorem, conjectured in 1637, was finally proven in 1995. 358 years, 14 generations of mathematicians, and finally, resolution. Andrew Wiles received numerous honors, including the Abel Prize, often considered the Nobel Prize of Mathematics. But in interviews, he often talks not about the glory, but about the journey. The problem, he says, was like entering a dark mansion. You grope around in the darkness, bumping into furniture, trying to figure out where you are. Occasionally, you find a light switch and a room illuminates, but most of the time, you're stumbling in the dark, and you have to have faith, even when you can't see, that there's a way through. The proof of Fermat's last theorem is one of the triumphs of 20th century mathematics. But it's not the only problem that has resisted solution for centuries. Let's turn now to a problem that remains unsolved, despite being nearly as famous, the Riemann hypothesis. Let's drift now to 1859, drifting back in time from Wiles's story to another century, another brilliant mathematician, another problem that will haunt generations. We're moving from one unsolved mystery to another, from a problem that was eventually conquered to one that remains stubbornly open. Bernhard Riemann was a German mathematician born in 1826 in the small village of Breselitz in the Kingdom of Hanover. He came from a poor family, the son of a Lutheran pastor, and his early life was marked by shyness and financial difficulty, but he showed remarkable mathematical talent from a young age. Riemann studied at the University of Göttingen, then the Center of German Mathematics, under the great Carl Friedrich Gauss. Gauss, one of the giants of mathematics, rarely praised anyone, but he recognized Riemann's extraordinary abilities. Riemann would go on to make fundamental contributions to several areas of mathematics, creating entire new fields almost single-handedly. He developed Riemannian geometry, which describes curved spaces, and would later become the mathematical language of Einstein's general relativity. He contributed to complex analysis, real analysis, and number theory. He introduced concepts that would shape mathematics for generations, and he died young, at just 39, from tuberculosis, leaving us to wonder what else he might have discovered had he lived longer. In 1859, when he was 32 years old, Riemann published a paper about the distribution of prime numbers. Prime numbers, those numbers divisible only by 1 and themselves, 2, 3, 5, 7, 11, 13, 17, and so on, had fascinated mathematicians since ancient times. The ancient Greeks knew there were infinitely many primes. Euclid proved that around 300 BCE with an elegant proof that's still taught in classrooms today. You assume there are only finitely many primes, list them all, multiply them together, and add 1. The resulting number isn't divisible by any prime on your list, which means either it's prime itself, or it's divisible by a prime you missed. Either way, your list was incomplete. Therefore, there must be infinitely many primes. But understanding how primes are distributed among the numbers, how often they appear, how the gaps between them behave, that remained mysterious. As you count upward through the numbers, primes become less frequent. Among the first 10 numbers, 4 are prime, 2, 3, 5, 7. That's 40%. Among the first 100 numbers, 25 are prime, 25%. Among the first 1,000, 168 are prime, about 16.8%. The proportion drops as you go higher. In the late 1700s, the brilliant young mathematician Carl Friedrich Gauss, then just a teenager, noticed a pattern. He conjectured what's now called the prime number theorem. The number of primes less than some number n is approximately n divided by the natural logarithm of n. This is an approximation, not exact, but it gets more accurate as n gets larger. Gauss's conjecture was finally proven about 100 years later, in 1896, independently by Jacques Hadamard and Charles de la Vallée-Poussin, but their proof raised as many questions as it answered. Yes, the primes roughly follow this pattern, but there are deviations, irregularities. Sometimes there are more primes than expected in a range, sometimes fewer. Understanding these fluctuations, these deviations from the smooth average, that was the deeper question. This is where Riemann's 1859 paper comes in. Riemann introduced a mathematical object called the Riemann zeta function. It's a function that takes complex numbers as input. Complex numbers are numbers that have both a real part and an imaginary part, like 3 plus 4 times IA, where I is the square root of -1. The zeta function is defined by an infinite series. You take 1 to the negative s, plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s, and so on forever, where s is your input number. This might seem like a strange thing to define, but zeta functions had been studied before. Leonhard Euler, back in the 1700s, had explored special cases of this function and discovered beautiful formulas connecting it to prime numbers. Riemann extended the study of the zeta function into the complex plane. He showed that the function could be analytically continued, meaning it could be defined not just for some values of s, but for essentially all complex numbers. And he discovered something remarkable about this function. The zeta function has certain special values where it equals 0. These values are called the zeros of the zeta function. Some zeros are obvious at the negative, even integers, -2, -4, -6, and so on. These are called the trivial zeros. But there are also infinitely many other zeros, non-trivial zeros, located in a certain region of the complex plane called the critical strip. The critical strip is the region where the real part of S is between 0 and 1. Within this strip, Riemann noticed something remarkable about the zeros he computed. They seem to all lie on a specific line, a vertical line in the complex plane where the real part equals 1/2. This line is called the critical line. Riemann conjectured that all the non-trivial zeros of the zeta function lie on this critical line. This is the Riemann hypothesis, and it's been unproven for over 166 years. Why does this matter? Because the zeros of the zeta function are intimately connected to the distribution of prime numbers. Riemann showed that if you know where all the zeros are, you can understand precisely how primes are distributed. The deviations of actual prime counts from the prime number theorem's predictions are controlled by these zeros. If the Riemann hypothesis is true, if all the non-trivial zeros really do lie on the critical line, then the deviations are relatively small and well-behaved. The primes are as regularly distributed as they could possibly be, given their overall decreasing density. But if some zeros lie off the critical line, the distribution of primes could be much more irregular, with unexpected clumps and gaps. The Riemann hypothesis would also confirm hundreds of other theorems that mathematicians have proved assuming the Riemann hypothesis is true. These conditional results are in a kind of mathematical limbo. They're probably true, and they've been proven under the assumption that the hypothesis holds, but they can't be considered absolutely certain until the hypothesis itself is proven. The Riemann hypothesis is considered by many to be the most important unsolved problem in mathematics. It's fundamental to number theory, and number theory in turn connects to countless other areas of mathematics and even to physics. In the year 2000, the Clay Mathematics Institute named 7 problems as their Millennium Prize problems, offering $1 million for a solution to each. The Riemann hypothesis was on this list, alongside other profound problems like P versus NP and the Poincaré conjecture. The Poincaré conjecture has since been solved by Grigori Perelman, though he famously declined both the prize money and the Fields Medal. The other 6, including the Riemann hypothesis, remain open. Mathematicians have checked enormous numbers of zeros of the zeta function. Using computers, they've verified that the first 10 trillion zeros and more all lie on the critical line, just as Riemann predicted. Every single zero that's been checked is on the critical line. But as with Fermat's last theorem, checking cases isn't the same as proving. There are infinitely many zeros to check, and a proof requires showing it's true for all of them, not just the ones we've tested. Many approaches have been tried. Some of the greatest mathematicians of the 20th and 21st centuries have worked on it. David Hilbert asked what question he would ask if he could wake up 100 years in the future, said he would want to know if the Riemann hypothesis had been proven. That's how central it is, how important it's considered. G.H. Hardy, the famous British mathematician, once said that if he could prove just one theorem before he died, it would be the Riemann hypothesis. John Nash, of A Beautiful Mind fame, worked on it. So did Alan Kohn, Michael Atiyah, Terence Tao, and countless others. All brilliant minds, all making contributions to our understanding, but none finding the final proof. There have been claimed proofs, of course. Just as with Fermat's last theorem, people periodically announce they've solved it. In 2018, the famous mathematician Michael Atiyah, who had won both the Fields Medal and the Abel Prize, the two highest honors in mathematics, gave a lecture claiming a proof. Atiyah was 89 years old and had an extraordinary career behind him. The mathematical community was excited but skeptical. Atiyah's claimed proof was short, remarkably short for such a profound result. He said it relied on insights from physics and on a concept he called the Todd function. But when mathematicians examined the details, they found the argument wasn't rigorous. There were gaps in the logic, undefined terms, appeals to intuition where proof was needed. The claim was respectfully but firmly rejected by the mathematical community. It was sad, in a way. Atiyah had made incredible contributions to mathematics over his long career. But the Riemann hypothesis wasn't going to be solved by a short, clever argument. If it falls, it will likely be to a long, technical proof using sophisticated modern mathematics, much like Wiles's proof of Fermat's last theorem. Other claimed proofs have similarly failed under scrutiny. The problem remains open, and yet progress has been made. Mathematicians have proven things about most zeros, about the density of zeros, about connections between the Riemann hypothesis and other mathematical structures. In 2024, two mathematicians, Larry Guth and James Maynard, made what some called a breakthrough on a problem related to the Riemann hypothesis, improving a result that had stood for over 50 years. It wasn't a proof of the hypothesis itself, but it was significant progress, showing that the problem isn't completely frozen, that new techniques can still make inroads. And here's something beautiful. Just as the quest to prove Fermat's last theorem generated entire new fields of mathematics, the quest to understand the Riemann hypothesis has driven advances in number theory, complex analysis, and even physics. The zeta function appears in quantum mechanics, in string theory, in statistical mechanics. The distribution of the zeros seems to be related to the distribution of energy levels in quantum systems. Physicists and mathematicians have found unexpected connections between the Riemann hypothesis and the behavior of elementary particles. The pursuit of this century-old problem continues to bear fruit, whether or not the hypothesis itself is proven anytime soon. Each partial result, each new technique, each insight into the structure of the zeta function adds to our understanding. We're learning about the nature of prime numbers, about the structure of the complex plane, about deep patterns in mathematics and physics. The Riemann hypothesis might be proven tomorrow, or it might remain unsolved for another century. Or, like some of the problems explored by Kurt Gödel, it might be unprovable within our current mathematical framework, true but forever beyond absolute proof. We don't know. And that uncertainty, that openness, is part of what makes it fascinating. Bernhard Riemann died in 1866, just 7 years after publishing his famous paper, never knowing how profoundly his conjecture would influence mathematics. He was in Italy, seeking warmer climate for his tuberculosis. When he died, he was 39 years old. His widow burned many of his unpublished papers following his instructions, and we'll never know what other insights he might have had. But the Riemann hypothesis lives on, a testament to his genius, a challenge to every generation of mathematicians since. 166 years and counting. And still, the zeros dance along their critical line, tantalizing us with their pattern, resisting every attempt to prove that the pattern continues forever. Now let's talk about a problem that might be the most dangerous of all. Not because it's the most important, but because it's so simple that anyone can play with it, and yet so difficult that it has trapped brilliant minds for decades. This is the Collatz conjecture, also known as the 3n+1 problem. It was introduced in 1937 by a German mathematician named Lothar Collatz. Here's the entire problem, expressed in a way that anyone can understand. Take any positive whole number. If it's even, divide it by 2. If it's odd, multiply it by 3 and add 1. Now take your result and repeat the process. Keep going. That's it. That's the whole problem. The conjecture says that no matter what number you start with, you'll eventually reach the number 1. Let's try an example. Start with the number 10. 10 is even, so we divide by 2 and get 5. 5 is odd, so we multiply by 3 and add 1 to get 16. 16 is even, so we divide by 2 and get 8. 8 is even again, so we get 4, then 2, then 1. We reached 1. Let's try another. Start with 7. 7 is odd, so 3 times 7 plus 1 is 22. 22 is even, so we get 11. 11 is odd, so 3 times 11 plus 1 is 34. 34 is even, giving 17. 17 is odd, giving 52. Then 26, then 13, then 40, then 20, then 10, then 5. And we've seen this sequence before. We know it reaches 1. Try any number you like. 3, 6, 15, 107, 3,492. Every number that's been tested eventually reaches 1. Some take a long journey. Some bounce up to much larger numbers before finally descending. But they all seem to reach 1. The problem is, nobody has proven this always happens. Nobody has found a counterexample either, a number that doesn't eventually reach 1. But nobody has proven that such a number doesn't exist. The Collatz conjecture has been verified by computer for all starting values up to more than 2 times 10 to the power of 68. That's a number with 69 digits, and yet a general proof remains elusive. The legendary mathematician Paul Erdos said about the Collatz conjecture, "Mathematics may not be ready for such problems." He meant that we might not yet have the mathematical tools needed to solve it. It might require entirely new ways of thinking. Another mathematician, Geoffrey Ligarius, called it An extraordinarily difficult problem, completely out of reach of present-day mathematics. Why is such a simple problem so hard? Part of the reason is that the behavior seems almost random. Some numbers reach one quickly. Others take a long, complicated path. There doesn't seem to be a pattern you can exploit. The problem is deterministic. The sequence for any starting number is completely determined, yet it behaves chaotically. There have been partial results. In 2019, Terence Tao, one of the world's leading mathematicians, proved that almost all numbers eventually reach a value below their starting point. This is significant progress, but it's not a proof of the full conjecture. Almost all in mathematics has a specific technical meaning, and it doesn't mean all. The Collatz conjecture remains unsolved, now for over 87 years, and it's considered dangerous because it's so tempting. You can start playing with it immediately. You don't need advanced mathematics to understand it or to explore it, but it has a way of consuming time, of leading you down paths that seem promising but go nowhere. It's the mathematical equivalent of quicksand, easy to enter but nearly impossible to escape. If you think the Collatz conjecture is old at 87 years, let me tell you about Goldbach's conjecture. This one dates back to 1742. In that year, a Prussian mathematician named Christian Goldbach wrote a letter to the famous mathematician Leonhard Euler. In it, Goldbach proposed the following idea. Every even number greater than 2 can be expressed as the sum of two prime numbers. That's it. Simple to state, impossible so far to prove. Let's test it with some examples. 4 equals 2 plus 2, and 2 is prime. 6 equals 3 plus 3. 8 equals 3 plus 5. 10 equals 5 plus 5, or 3 plus 7. 12 equals 5 plus 7, and so on. The larger the even number, the more ways there usually are to write it as the sum of two primes. 100 equals 3 plus 97, or 11 plus 89, or 17 plus 83, or 29 plus 71, or 41 plus 59, or 47 plus 53. At least 6 different ways. Mathematicians have checked this conjecture by computer up to enormous numbers. It's been verified for all even numbers up to 4 times 10 to the 18th power. That's 4 followed by 18 zeros, a number so large it's hard to comprehend. And yet, no general proof exists. Why is this hard? The problem is that prime numbers seem to be distributed almost randomly. There's no simple pattern to where they appear. Yes, we know theorems about the approximate density of primes, but predicting exactly where individual primes are is extremely difficult. Goldbach's conjecture asks us to show that for any even number, somewhere out there in the infinite landscape of primes, there are always at least 2 that add up to that even number. As the numbers get larger, there are more primes available, so you'd think it would get easier. But proving it works for every even number, all the way out to infinity, requires a level of control over prime numbers that we simply don't have yet. There's a related problem called the weak Goldbach conjecture. Every odd number greater than 5 can be written as the sum of 3 primes. This one was proven in 2013 by Harold Helfgott, after being open for over 270 years. But the strong form, the original 2 prime version, remains unsolved. Goldbach's conjecture has now been unsolved for 283 years. That's older than the United States of America, older than the French Revolution. Mozart wasn't even born yet when Goldbach first proposed it, and we're still working on it. Let's take a moment and consider what these problems have in common. Fermat's last theorem, solved after 358 years. The Riemann hypothesis, unsolved after 166 years. The Collatz conjecture, unsolved after 87 years. Goldbach's conjecture, unsolved after 283 years. They're all easy to state. You don't need a PhD in mathematics to understand what they're asking. A bright high school student, or even a middle school student, could grasp the question. And yet, they resist solution with a stubbornness that seems almost willful. Part of the difficulty is that these problems sit at the edge of our mathematical tools. We can approach them, get close, prove special cases, verify millions or trillions of examples. But the final proof, the argument that works for all cases, requires something we don't yet have. Maybe it's a new technique. Maybe it's a connection between different areas of mathematics that we haven't noticed. Maybe it's a completely new way of thinking. Fermat's last theorem was proven only when Andrew Wiles found a bridge between modular forms and elliptic curves, two areas that seemed completely unrelated. The proof requires mathematics that literally didn't exist in Fermat's time. It uses complex analysis, algebraic geometry, representation theory, sophisticated tools from multiple fields. This is almost certainly why Fermat's claimed proof didn't exist. He couldn't have had the tools to prove it. The unsolved problems might be similar. We might be waiting for mathematical innovations that haven't been invented yet. But there's another possibility, one that's a bit unsettling. Maybe some of these problems are actually unprovable. Not false, but unprovable within our current mathematical frameworks. This isn't as crazy as it sounds. In the early 20th century, Kurt Gödel proved his famous incompleteness theorems, which showed that in any sufficiently complex mathematical system, there are true statements that cannot be proven within that system. Some mathematical truths are, in a sense, forever beyond proof. Could the Collatz conjecture be one of these? Could Goldbach's conjecture? It's possible. John Conway, the mathematician famous for inventing the game of life, proved that certain Collatz-like problems are actually undecidable. They cannot be proven or disproven using the standard axioms of mathematics. The original Collatz conjecture might not be undecidable, but the fact that closely related problems are undecidable suggests we should be humble about what's possible. If these problems are so hard, if they've resisted centuries of effort, why do mathematicians keep working on them? Part of it is simply the challenge. These problems have a way of getting into your head. You start thinking about them, and you can't stop. Andrew Wiles said that even when he wasn't actively working on Fermat's last theorem, it was always there, a constant background hum. Part of it is the hope of glory. If you solve one of these century-old problems, your name goes into the history books. You become part of mathematical folklore. Wiles is famous not just among mathematicians, but among the general public. How many other number theorists can say that? But there's something deeper too. These problems are beautiful. There's an aesthetic appeal to them, a sense that understanding them would reveal something profound about the nature of mathematics. and reality itself. And crucially, even failed attempts at solving these problems often generate valuable mathematics. Ernst Kummer's work on Fermat's last theorem created the theory of ideals, which became fundamental to modern algebra. The attempts to prove the Riemann hypothesis have advanced our understanding of prime numbers, complex analysis, and even quantum physics. The journey itself is valuable, even if the destination remains out of reach. Mathematics isn't just about answers. It's about the questions, the methods, the connections, the new ways of thinking that emerge when you grapple with hard problems. Consider what we've learned from Fermat's last theorem alone. The proof required creating bridges between completely different areas of mathematics. It showed that elliptic curves and modular forms, objects that seemed entirely unrelated, are deeply connected. This insight has implications far beyond Fermat's last theorem. It's changed how we think about the structure of mathematics itself. The Riemann hypothesis has inspired similar cross-pollination. Ideas from physics have been applied to questions about prime numbers. Techniques from one area of pure mathematics have illuminated problems in another. The hypothesis sits at the center of. There's also something deeply human about these problems. They represent our desire to understand, to know, to find certainty in an uncertain world. They're monuments to human persistence and ingenuity. Think about Sophie Germain, teaching herself mathematics in secret, making breakthrough contributions despite facing systematic exclusion from the mathematical community. Think about Andrew Wiles, working in isolation for 7 years, sustaining focus and determination through countless dead ends and frustrations. Think about all the mathematicians whose names we don't know, who worked on these problems, who made small advances or hit dead ends, but who kept the torch burning and passed it to the next generation. These problems are stories, human stories, about obsession and dedication, about the joy of discovery and the agony of failure, about communities of people across centuries working together even if they never met toward a common goal. When Wiles announced his proof in Cambridge, mathematicians in the audience were in tears, not because a theorem had been proven, but because they were witnessing history. They were present for the culmination of a quest that had spanned more than 3 centuries. They were there when the question mark finally became an answer. And for the problems that remain unsolved, there's still hope. Somewhere, maybe a young person is reading about the Riemann hypothesis or the Collatz conjecture for the first time. Maybe they're feeling what Wiles felt when he was 10 years old reading about Fermat. Maybe they're making a promise to themselves, a promise that will drive them for decades, a promise that might eventually be fulfilled. So we wait, we work, we hope. The Riemann hypothesis remains unsolved, now entering its 2nd century of resistance. The Collatz conjecture continues to baffle, simple yet stubborn. Goldbach's conjecture approaches its 300th birthday, still unproven. But mathematicians continue to chip away at them. New techniques are developed, partial results are proven. The landscape of mathematics shifts slowly as new connections are found and new tools are forged. Maybe tomorrow, someone will announce a proof of the Riemann hypothesis. Maybe it will take another 100 years. Maybe it will never be proven at all. We don't know. But that's okay, because mathematics isn't just about the destination. It's about the journey, the exploration, the gradual accumulation of understanding. These century-old problems are lighthouses, beacons that guide mathematical research. They give us direction, purpose, motivation. They remind us that there are still mysteries in the universe, still frontiers to explore, still questions that can humble us with their depth. In some ways, the unsolved problems are more valuable than the solved ones. They keep us honest. They keep us curious. They remind us that no matter how much we know, there's always more to learn. As we approach the end of our journey tonight, let's think about what the future might hold. New problems will emerge, certainly. Mathematics is constantly growing, and with new areas come new questions. Some of today's cutting-edge topics might become tomorrow's century-old unsolved problems. But for the problems we've discussed tonight, the ones that have already stood the test of time, what happens next? The Riemann hypothesis might be proven in our lifetime. The tools are getting better. Our understanding is deepening. Or it might remain unsolved for another century. Or it might be one of those Gödelian statements that can never be proven. The Collatz conjecture might similarly be proven or shown to be undecidable. Or it might sit in limbo for generations more. Goldbach's conjecture has survived for nearly 300 years. It might survive for 300 more. Or everything could change tomorrow. A new insight could crack open one of these problems. A young mathematician somewhere could be having the realization that leads to a solution, and we just don't know it yet. That's the beauty and the frustration of mathematics. Progress is unpredictable. Breakthroughs can come from unexpected directions. Andrew Wiles solved Fermat's last theorem by connecting it to something that seemed completely unrelated. The next big solution might come from an equally unexpected place. And if you're interested in these problems, if you're curious about mathematics, know that you don't have to be a professional mathematician to appreciate them or even to think about them. These problems belong to everyone. They're part of our collective intellectual heritage. You might not solve them, probably won't if we're being realistic, but thinking about them, playing with them, learning about the history and the attempts and the partial progress, that's valuable in itself. It's a way of connecting with centuries of human thought, of participating in one of humanity's great ongoing projects, the quest to understand. As we prepare to drift off into sleep, let's return to where we started. A margin note in a book, 358 years of struggle, and finally, a solution. A hypothesis about prime numbers, 166 years and counting. A simple iterative process, 87 years of mystery. A conjecture about sums of primes, 283 years and still going. These aren't just mathematical problems. They're threads running through history, connecting generations of thinkers, inspiring new mathematics, driving innovation, humbling us with their difficulty, and occasionally gloriously, finally yielding to human persistence and ingenuity. They remind us that some things are worth pursuing even if we never reach them, that the journey can be its own reward, that mystery and uncertainty are not weaknesses, but features of a rich and complex universe. Tonight, as you drift off to sleep, maybe you'll dream about margin notes and prime numbers, about sequences that spiral up before falling down, about sums and conjectures and century-old mysteries. Maybe you'll dream about the mathematicians who devoted their lives to these problems, or about the moment when a proof finally comes together and a question mark transforms into a period. Or maybe you'll just sleep peacefully, with a quiet appreciation for the fact that there are still things in this world that we don't understand. Still problems that can unite people across centuries in a common quest. Still mysteries waiting to be unraveled. Thank you for joining me on this gentle journey through some of mathematics' greatest mysteries. If you enjoyed this exploration into equations that take centuries to solve, I hope you'll consider giving the video a like and subscribing for more relaxing mathematical journeys. Your support helps keep this channel growing and allows me to continue creating these peaceful explorations. From all of us here at Math for Sleep, may your dreams be filled with wonder, your rest be deep and peaceful, and your curiosity remain alive and well. Good night.